Hello and welcome to a CNCM lecture on geometric probability by me, Akshay Churla. And so let's get started. So what is geometric probability? So we have a normal probability over here. And so you've probably seen probability like this. Probability is equal to the number of successes or the number of possibilities. It's not all how all probability is expressed as, but it's how a majority of it is expressed as and how it's originally taught. And so in terms of rolling a die, it's really easy. Like, what's the probability that you roll a 1 on a regular six-sided dice? Well, you have one success, six possibilities, so 1 over 6. Pretty easy. So geometric probability isn't too different compared to this. And these are the case when there is an infinite number of successes and or possibilities. And we deal with that by using geometric concepts. So let's take, for example, the next problem here. And you have, what is the probability that when choosing a random real number between 0 and 6, your number is between 0 and 1? Now, for some of you, you may just say 1/6. It's kind of obvious, right? But it may not be that clear. First of all, if you want to do the number of successes or the number of possibilities, there's an infinite number of successes and an infinite number of possibilities. Because there's an infinite number of real numbers between 0 and 1, and an infinite number of real numbers between 0 and 6. So how do you express this? And for the people that said 1/6, they considered length. Let's take, for example, a number line. We have a number line right here, and you got a 0, 1, 2, 3, 4, 5, and 6. And so this number line represents our possibilities because any number, any real number will be on this number line. You could pick something like pi. It's going to be somewhere over here, right? And so we represented all the real numbers from between 0 and 6 on this number line. And we want to know what's the probability of choosing a random real number between 0 and 1. What's the probability of that? And this segment, if I can use a different color here, I'll try. This segment right here, that is the one we want. So in terms of probability, how do we approach this? We don't have the number of successes over number of possibilities approach, but we can use a geometric concept, and that's length. V, we're able to represent every real number between 0 and 6 and 0 and 1 with this number line, and this number line has length, and it has length 6. It's length 6, that's the length that represents all the possibilities. And the success is between 0 and 1. That has length 1. And for that reason, our probability is 1/6. And some of you may not have gone to this explanation as your immediate explanation, but you're basically using geometric probability when you immediately say 1/6, because to represent an infinite number of possibilities, this is what you do. But I want to make it a bit more complicated. Given that the real numbers x and y are chosen from 0 and between 0 and 1, what's the probability that x plus y is greater than 1? Well, we don't know. We can't use a number line this time. Why can't we use a number line? Because there's two variables and it's hard to plot. Well, we could use a number line in some cases, but here, if you try, it's going to be a bit complicated because you actually can't express a sum. Um, if there's like a difference between them and you want to find like if the difference is greater, then you can actually see that number line will be useful, and we'll cover that soon. But in terms of the sum, we can't really express that on a number line. And so, how do we express the sum? How can we convey this infinite number of successes and infinite number of possibilities? Well, we could use number line's one dimension, so what about the next dimension? Two dimensions. I mean, we have two variables, x and y. They correspond to the coordinate plane. So what if we just made a coordinate plane and see what happens then? This would be the x plane. This would be the x-axis. This would be the y-axis. And now we know that x and y are chosen between 0 and 1. So in terms of that, this is going to be the origin. Uh, and so this is going to be, I'm going to put a 1 here. And so this square right here represents all the possible pairs of x and y that we can choose. Just like the number line represented all the values of that random number. This represents all the possible values of all the possible values of what x and y could be. And so this is the area of our possibility. And it's a square with area 1. And so I guess you can make our denominator 1. But we want to find the probability that x plus y is greater than 1. Now we have a coordinate plane over here. And you can graph inequalities on a coordinate plane. And we can graph this inequality right here. This is going to be y is greater than 1 minus x. The equation y equals 1 minus x is going to be this line right here. So it's going to be, let me use a different color. It's going to be this line over here. And you can, I'm going to shade it in. This is going to be the part where x plus y is greater than 1, because this is the side of the line where x plus y is greater than 1 in terms of graphing inequalities. If you're not too comfortable with graphing inequalities, you can find some good resources online on how to do that. Actually, this whole region out here also, like anything across this whole line works, but I'm just considering the intersection of this line in our square, because x and y can only be along the square, right? Like they can only be in this square. So this area right here corresponds to x and y being in that range or domain 0 to 1, and this blue area is where x plus y is greater than 1. So this is our area of success. This is the success. And so the area of success is simply 1/2. Half the square is shaded, and the area, the square has area 1. Or you can just, this triangle has side length 1 here, side length 1 here, multiply, divide by 2, 1/2. You get a 1/2. So the probability is going to be 1/2 because the success area is 1/2. The possibility area is 1, so 1/2 divided by 1, that's 1/2. And so if I move on, we're going to go over some more complicated examples. Before I do, I just want to go over a small note here. You can do this geometric probability you can also do it for 3D problems. I'm not going to cover 3D problems in this lecture. They don't show up as often, geometric probability with 3D. Well, they do show up a little bit often, but you won't see them too much. But it's going to work the same way. You're going to visualize a problem with 3 dimensions. And the hardest part of problems like that is just visualization. Visualization can be a little bit challenging with 2D, but it's going to be more challenging with 3D. The best thing to do is practice. I'll try to find some POTDs that have 3D probability, 3D geometric probability. So, and I can go over those solutions later. But let's do some worked out examples. I have 3 of them. They're going to take us a while to do. So let's start with this one. 2018 AMC 10B number 22. So it's already a late problem on the AMCs. And so the real numbers x and y are chosen independently and uniformly at random from the intervals 0 to 1. And that interval is showing up again. And which of the following numbers is closest to the probability that x, y, and 1 are the side lengths of an obtuse triangle? Before we deal with this whole triangle condition, look at this. This statement we've already, okay, I'm kind of crossing stuff out here, but this statement, real numbers x and y are chosen from this interval, we've already covered before. This is going to be that coordinate plane. And I know just denote this with the 1, this with the 1. It's going to be a y-axis. It's going to be an x-axis. And so there you go. You already have your possibilities here. But with this problem, there's 2 conditions. We need, with the words obtuse triangle, we need, first of all, we need x, y, and 1 to form a triangle. And then we also want it to be obtuse. For it to form a triangle, we know that we can just use the triangle inequality. This has 3 equations. X plus y is greater than 1, x plus 1 is greater than y, and y plus 1 is greater than x. With the equation x plus 1 is greater than y, x and y are both going to be at max 1. So x plus 1 is greater than y is always going to be true, and y plus 1 is greater than x is always going to be true. So really the only equation we have to worry about is x plus y is greater than 1. And we've already done this problem. I'm not going to go over it again. But if I go ahead and pick a blue color here, we already determined that there's going to be this, if I can draw this a little bit better, this shaded area right here. By the way, I'm only considering area within the square. Um, and so we got that condition down, but they want to know about an obtuse triangle. And so how do we do that? If you're not sure with this, there are proofs for this. To form an obtuse triangle with sides ABC with A less than B less than C, you have to have that C squared is greater than A squared plus B squared. This is related to the Pythagorean theorem. Obviously, the equality case means it's a right triangle, but this is the condition for an obtuse triangle. And in terms of x, y, and 1, this means that 1, because 1 is going to be the greatest side length, is going to be greater than x squared plus y squared, which means that x squared plus y squared is greater than 1. Now here, it might be a bit hard to visualize, but this is the same thing as graphing the inequality x plus y is equal to 1, greater than 1. It's similar. If we don't recognize this form, if you write it as x squared plus y squared equals 1, that's a circle. That's the equation of a circle with radius 1 centered at the origin. So, and the area that is, oh, by the way, I messed up my sign here. I'm sorry. It's supposed to be less than, it's going to be less than, let me erase this part. It's going to be less than 1. I don't know. Yeah, so since 1 is greater than x squared plus y squared, x squared plus y squared is going to be less than 1. So we can start by drawing out the outline of a circle. I'm going to use green, I think, for this. And I'm only going to consider the quarter circle that's in the square. I know like the whole square is gonna like I didn't mean to draw there. Whole square is gonna span like this whole plane, but I'm only gonna consider the part that's in the square because that's the only possibilities for x squared and y squared. And so I'm just gonna draw this in here. And for x squared plus y squared to be less than 1, you can take an example point, like the origin 0 is less than 1. So it's gonna be this whole area in here. Now we want both of these to be true at once. So the only area that corresponds to both, and I'll use a darker, way darker blue for this, is going to be this small circular section right here. It might be a bit hard to visualize. I'm going to outline it. I'll try my best. This outline right here. This part of the circle is the area we want. How do we find that? Well, first of all, we can see that the area of this quarter circle is going to be the area of the whole circle divided by 4, and the area of the whole circle is just pi, since the circle with radius 1. So it's pi over 4. Now, then we can just subtract the area of this triangle over here, this triangle right here. And this triangle has area 1/2, side length 1, so subtract 1/2. Now we want to find which of the following numbers is closest to the probability. Pi over 4 is about 0.79. You can do the calculations to verify that. 1/2 is 0.50. If you subtract that, you're going to get 0.29. So we have our answer right here, C. And so that problem is finished. Not too complicated, simple geometric probability. So let's move on. Our next problem is the 2019 AMC 10A, number 22, 12A, number 20. And it says, real numbers between 0 and 1 inclusive are chosen in the following manner. A fair coin is flipped. If it lands heads, then it's flipped again, and the chosen number is 0. And if the second flip is heads, and one is and one of the second flip is tails. On the other hand, if the first coin flip is tails, then the number is chosen uniformly at random from the closed interval 0 to 1. Two random numbers x and y are chosen independently in this matter. One is the probability that x minus y is greater than 1/2. First of all, this is a lot to take in. We can see that we're choosing x and y in some strange manners. So these coin flips all mean something different. So let's see what happens if we flip. We're going to take our first coin flip only, and we'll see how x and y are chosen. Let's say we're both chosen by flipping heads first. That means that uh, When we flip heads, we're going to have a 1/2 probability of getting a 1 or a 1/2 probability of getting a 0. So all these are likely to happen. The first number can be 1, second number can be 0, and these are all the possibilities for what x and y can be in this case, because there's a 1/2 probability of it being 1 or a 1/2 probability of it being 0, the number that we pick using this method. So, well, we want to know that the our success is going to be, this, right? And so x minus y is greater than 1/2. Only two of these four cases work. So it's going to be a 1/2 probability for this case. And this probability, by the way, occurs with probability 1/4, of course. You're going to flip. And so, like, you can only flip two heads, it's probably 1/4. And so that's going to be 1/8. Now let's go HT, heads and tails, or tails and heads. I'm going to lump these into one case because they're very similar. Um, if we pick, let's say we pick x with, and we'll multiply by 2 at the end to account for the two cases. Actually, no, I'm not going to do that because we're already going to multiply by 2 with, yeah. So let's just take, for example, the HT case. Let's say we pick x to be 1. X is going to be 1 or 0. Let's say x is equal to 1. If x is equal to 1, then y has to be, then the difference has to be greater than 1/2. If you take this number line right here, 0, 1, and I'll put 1/2 right here, you can see that x is going to be here. And we want y to have a difference with x, absolute value difference with x that's greater than 1/2. Now, there's a number line here because we're talking about difference, as I was talking about before, and it's kind of easy to visualize difference on a number line because we can see how far apart two numbers are using a number line. And so let me find the success area for y. We can't put y anywhere here, but we can start to put it right here because, and we can do it across this whole area. And that's because if you put y anywhere here, then obviously the difference is going to be less than 1/2 because y is going to be greater than 1/2. So the difference is going to be less than 1/2 between the two numbers. But past 1/2, the difference will actually be 1/2. Yeah, the difference will actually be greater than 1/2. Sorry. So the probability that this occurs is 1/2. That y gets chosen like that. So yeah. So and it's going to be the same thing for the other case. So I'm going to multiply by 2. So you're going to have 2 for both the cases. 1/4 chance of flipping each of them. This 2 accounts for both the flips. And then you're going to multiply by 1/2. You're going to multiply by 1/2 here. And that's going to give you 2 times 1/8, which is equal to 1/4. So far, our probability with these two cases is 1/8 plus 1/4 is equal to 3/8. There's one more case, obviously the tails case. I'm going to cover that on the next page, and then we'll come back to this. So we've come back, and our probability is 3/8 so far, and we have to cover one more case, and that's the tails case. And now this means that both numbers are chosen randomly between 0 and 1. And in this case, I know that I told you that difference is kind of easy to visualize on a number line, but the reason I did that is because x was fixed. And so we could just range y over. But this time, since x and y can be anything, we actually have to go ahead and use a coordinate plane. So, and you can try, using an number line first and see that it won't work as well. Then you can flip to the coordinate plane if you're having a bit of trouble understanding the concept here. I may have misspoken at some point, but yeah. If you're just ranging one number, you can use a number line. See, as I said, x, we fixed x, but we were ranging y. And so since we're only really changing one variable, that's why we're able to use the number line. But here we're changing two variables, so we got to use this. So obviously our square of possibility comes back into play again. And this time we want to see that the absolute value of the difference is greater than 1/2. So what I like to do with a problem like this is it's kind of hard to graph inequalities. You could actually split them up and that would actually work. But I'm going to show you a different approach that could be more useful and more applicable to problems when you're not sure how to approach something like this. You can definitely go ahead and, graph the inequalities. X minus y is greater than 1/2, and x minus y is greater than, it's going to be like greater than negative 1/2, I believe. Let me make sure. Yeah, I believe that is correct. Hmm. Yeah. So I could graph those two inequalities, but I'm not going to. So I'm going to do a different approach. So let's say that x was 0. Let's say we fixed x to be 0. Then what would the possible values be for y? Well, let's fix this to be 1/2 right here. Well, as you said in the number line, these are like mini number lines, right? Like they're vertical number lines. We can see that this is going to be the area that's going to correspond to the difference being greater than 1/2. Let's say x is something like 1/4. In this case, then we know that y has to be at least 3/4, um, or else the difference won't work out. And so 3/4 is going to be there. And let's say x is equal to 1/2. Well, then y can only be, well, it can't be anything. It's going to go off to here. It's going to be really close to 1. Like any number really close to 1 is going to hit there. Let's say x is like 3/4 again. And also, by the way, y can also be like really close to like 0 from the negative side. Let's say x is 3/4, then you can see that, well, y can be at least 1/4, right? But, I mean, at max 1/4, but it has to be less than that. And, this is going to go up vertically if you try numbers in between here. And just like that, if x is 1, then y has to be 1/2 or less. Well, less than 1/2. And so you're going to have this area here. And this is a success area. And you can calculate the probability, you can calculate the areas out. The total area here is going to be 1/4. A cool way to see it is that if you like merge these triangles together, it's going to form like a quarter of the square. I didn't mean to draw that. So the probability here in this case is actually 1/4. Let me switch colors. So the probability, I'll say our numbers being different, our numbers, or the difference of our numbers being greater than 1/2 is 1/4. Well, the probability of this case occurring right here is 1/4, because flipping two tails, probably that is 1/4. So we have 1/16 here. And if you add that to our running probability of 3/8, you're going to get that the sum of this is going to be 7/16. And that is our answer, and it is B. And for today, we have one last example to go over. 2015 AMT 10A number 25. Let S be a square of side length 1. 2 points are chosen independently at random on the sides of S. The probability that a straight line distance between the points is at least 1/2 is A minus B pi over C. And you want to find the sum of that. A plus B plus C. So first of all, let's take this square. Now, you're going to pick points in the chosen sides independently, and so we can break it into casework. First of all, the 2 points could be on the same side. So that's one case, the same side. Or they could be, use a different color to represent this. They can be on opposite sides. And that's going to be opposite. Or they can be on adjacent sides, like this and this. So we get adjacent. Those are our three cases to work with here. And we'll see what the probability is for each case occurring. Let's say you fix a point here, let's say we fix this point over here, the probability that uh, the next point's going to be, since they're chosen independently, probably the next point's going to be on the same side is 1/4 because it has to be landed on the same side. Only one side works out of the four, so this has probably 1/4 of occurring. Opposite side has a probability of 1/4 as well because there's only one opposite side to the point you fix, which is this side, and so this would be, let's do 1/4. And finally, for adjacent, if you fix this point, you can see that you can either have this side or this side to be the adjacent sides. So that's going to be 1/2. So those are the weightings, the probabilities. Is what we're going to multiply what we get for each of them. So let's start working out the cases. So let's work out the same side case. The same side case, you have square here. I drew it way too big, but let me clear this up. I don't need that big of a drawing. Let's say we have a square like this. In this case, we're picking our 2 points here, and we want to know that we want to find the probability that the distance between them is at least 1/2. We've recognized this problem before, haven't we? We have. In fact, this is actually the exact same thing we did here, and I'll tell you why. Let's think that this side right here is a number line. And so the points we pick, let's say the first point is x and the second point is y, we're going to find if the difference between them, obviously they can be the other way around too. We're going to find the difference between these two is greater than 1/2. And we've already computed that probability. We've computed it right here. And we know that this probability is going to be 1/4. So I don't have to do it over again. It's the exact same problem as this one right here, which is nice. So the probability for this case is 1/4 that the two points differ by a distance greater than 1/2. And in terms of the overall probability, the points being on the same side, that happens with probability 1/4 overall. So our sum for this case is going to be 1/16, our result. So what if they were on opposite sides? In this case, oh, my thing glitched out. Don't know why I drew something there. There we go. So we have this and we have opposite sides. Now the thing with opposite sides is that if they're on opposite sides, they're always going to have a difference greater than 1/2 because their difference is always going to be at least 1. You either have a straight line distance or you're going to have like a sloped distance here, and it's always going to be greater than 1/2. So it's always going to happen. If two points are on opposite sides, they're always going to have a distance at least 1/2. So, and the probability that this case even happens is 1/4. And so our overall probability for this case is 1/4. Give me a second here. My mouse is not working for some reason. There we go. Okay. So now our final case we want to deal with is this adjacent side case. So we have adjacent. Now this is going to be just a little bit more complicated. And so in this case, let's consider something here. We can see that this point is going to be a distance of, let's say, A away from the origin, this point. And this is going to be B away. And so the distance here is going to be A squared plus B squared. And so A and B are chosen between 0 and 1 randomly in this case. We can let this be 0, 1, and 1. So in this case, we want A squared plus B squared to be greater than or equal to 1/2, because it has to be at least. And this corresponds to A squared plus B squared is greater than or equal to 1/4. And in terms of our area, we can let this be the A and this be the B. We can see that this is a circle with radius 1/2 centered at the origin. And so this area right here, it's going to be 1/2, it's going to be 1/2, is going to be, it's not going to be this area actually. It's going to be the area outside of this. Let me fix that. It's greater than or equal to 1/4, so it's outside the circle. And so this is going to be the successful area. And so this is going to be 1 minus pi over, so the area of the whole circle is pi over 4, and you divide that by 4 because it's a quarter circle, be pi over 16. And you multiply this by 1/4. Because, actually, you multiply this by 1/2 because that's the probability of having 2 points being on adjacent sides in this case. So that is going to give us 1/2 minus pi over 32. And now we just have to add these all up to get our answer. I have another thing set up. Just transfer these over. We have 1 over 16 plus 1 over 4 plus 1/2 minus pi over 32. We can get a common denominator of 32 here. So that's going to be 2 plus 8 plus 16 minus pi over 32. And that's going to be 26 minus pi over 32. That's going to be our answer. And going back all the way, our answer is 26 minus pi over 32. That means that A is 26, B is 1, and C is 32. And thus our sum is going to be 59, which is A. And that is the problem. Thank you for watching this lecture. If you haven't already, you should join the CNCM YouTube channel, CNCM Discord server, not the YouTube channel. You should join the CNCM Discord server. I'll try to put a link in the description below. And that is it. If you enjoyed this video, please like and subscribe. Uh, in our CNCM Discord server, we have POTD daily competition problems. And this week, obviously, the upcoming week is going to be problems on geometric probability. So if you want to practice your skills, then I encourage you to join and participate in that. And that's really all I have for today. Thank you for watching, and I'll see you next time.